apologize for the faculty here that need to see this talk every year, and it's not that I don't have a new matter, only that Eliezer insists that I give that very classical talk on material that is so fundamental, and it actually, in a way, it relates to talk that was given by Siavash when you saw the top of this tree that he drew on super tree. So this is the root. Okay, so everything deviated and evolved from here. So like I said, starting from the basics. Okay, so yeah, let's start. So this is a phylogeny, and by coincidence, it's the same slide that Siavash he took from his advisor, and I took from his advisor as well. So a phylogeny is represent the history of the species at the leaves, okay, at the leaves of this tree, and the leaves are these living species or extant species, and internal node represent either extinct species or speciation events. Okay, this is also, it depends how we see how we view the tree. It's now everything is more abstract, more mathematical, but for now, let's look at it. So let's review the talk outline. So I'll start with the basics of the supertree construction. Then I'll start from the basics of supertree, which is the mean cut approach. And I will introduce the max cut. I will move to theoretical results on quartet approximation or quartets what are quartets, why we need to approximate. Then I will return back from theory to biology and will just touch the topic that also was addressed in the retreat, if you remember, which is tree distances. Then I will conclude. Okay, not too much technical details, although there is a lot. Okay, so what is supertree construction? So standard phylogenetics, so that goes, if you follow to Tandy Warnow's important talk about alignment. So you can see it as an alignment. It's the most basic thing in comparative genomics, and so we take autologous sequences, like sequences that come from a given gene, gene A, and we take that gene from all these organisms and we compare them. However, not always we have from all our organisms that gene. So from this set of species, we have gene A, and from this set, we have gene B. And moreover, sometimes we also have for another subset of our species set, we have some other signal, evolutionary signal. We want to combine all these signals on the form of sequences, on the form of morphological, on the form of anything. We want to use all this data and to construct one big tree over the entire species set. Okay, so this is the supertree task, and to combine all these signals into that summarizing or to that concluding history. Okay, let's see a very some illustrative example. So we have these three trees that were constructed somehow over that species set, and you want to combine them. So what we do is we take there is some signal here, evolutionary signal, mathematical signal, you can look at it, and combine it together to get that that tree. And it can be shown mathematically, it can be shown that they really yield bijectively that tree, meaning there is no other tree. Okay, so let's start now with some very fundamental distinction. So we have the rooted and the unrooted setting. So in a rooted setting, it is more or less the way the history was proceeded, okay, which we have ancestor, which is a root, and then and then we have the descendants and children. And so trees here, the mathematical definition here is least common ancestor. Okay, so we have the ancestry relationship, and the basic information, the most basic information is a rooted triplet. We will see very soon what is the signal here. However, in the unrooted setting, that is not the true history, because we don't have the time notion, this is the setting. So this is the unrooted setting. We don't have the time notion. We don't have ancestry here. We have here splits. So when we take an edge from a tree, the tree is now disconnected, and we have splits between set of taxa. Some guys in one side, on one subtree, the other guys in the other subtree. And here the most basic signal is a quartet, okay, which means, so here it means that the common ancestor of this guy, the least common ancestor, is later than the entire triplet. Where here we say there is a past, no time, no before, no after, no ancestry. There is a past separating these guys. They can be very, very far apart, but they are separated from these guys. We will see some examples where very non-intuitive, which makes all this field of the unrooted setting very hard. Okay, so what is the underlying supertree approach? Given input trees of various sizes, okay, like we see here, like we saw before, we decompose them into the most basic units. Okay, so here we have these 6 triplets, okay, and now we have some form, we know how to combine triplets. So we combine them all together, and we get the tree that satisfies all these triplets. Okay, let's now review. Let's review how we do that. It's very cute algorithm that so this is not all. So also, again, it goes to Siavash talk that sometimes we want to construct very accurate trees over small subsets. We have like millions. Again, it goes to Siavash. So Siavash talk about from the ground on real examples. So he comes with huge data sets of millions. He decomposes them. He constructs accurate trees, and then he combines them. Okay, how he combines? Exactly this way. Or they have their own software that he spoke, but it's this general idea. You decompose overlapping subsets, you reconstruct the trees, and now you deal with trees, not with sequences and not with signals. So now you deal with trees, which is supposedly more easier. Okay, so very surprising result that was found after some investigation, not myself, is this very cute algorithm that came actually from database theory, okay, that works recursively by a divide and conquer. And this is actually the underlying, the divide and conquer is the underlying approach in supertree whatsoever. Okay, so it constructs some connectivity graph over the set of taxa and then connects that connectivity graph according to connected and partitioning them according to connected components. Let's have a look. Okay, so we have these guys, and this is the connectivity graph. This is the connectivity graph. So we have, these are the vertices, and now we have these two guys. So I don't know if you see them, but we connect them here. These two monkeys, we connect them. Okay, so let's look at more symbolic examples. So we have these 6 triplets over this species set of 1 to 6, and now so we construct a connectivity graph like you see here. So we have these vertices, and now go a triplet by triplet. So we start with the first one, with the leftmost triplet, and we connect 1 and 2. Okay, so we connect 1 and 2. And now we connect 2 and 3. You see, 2 and 3. Now the middle triplets, 4 and 1. And now 1 and 3. And now 6 and 5. So this is our connectivity graph that was constructed constructed on the species set. This is the species set, and this is our phylogenetic signal. Okay, the triplets are the signal. Now let's see what we do. Now we introduce a new, so while we construct this connectivity graph, we also sort of composing the tree on the other side. Okay, so this is the tree. So we have a new tree node U, and let's see over what we have. So we have that connected component from the connectivity graph here, and that connected component. So a connected component is again recursively the species set and the triplets and the phylogenetic signal. Empty set here, and here this is the species set and the phylogenetic signal, the triplets that goes into here, that go into here. Okay, let's continue. So on the right, we just hang 5 and 6. 5 and 6 on the right. And now let's see what we do recursively on the left. So we have 1, 2, 3, 4. Let's construct the connectivity graph. 1, 2, 3, 4. And now, who can tell me what edges we add here? 1 and 2, correct? And now 2 and 3. Our connectivity graph. What are the connected components? This and this. So we hang 4 on the right, on the left, it doesn't matter. And again, recursively, 1, 2, 3, and that triplet, 1, 2, 3. Let's apply that algorithm recursively. No need to do that. Let's just see. We just hang that 1, 2, 3 here. Okay, a tree node, that tree node from before, 4 here, and this is our subtree. Now we return in the recursion. We go up, we unfold. This is the entire tree. This is the tree that satisfies that instance. And the instance is just a set of triplets. Okay? That's it. So this is AHO algorithm. Very famous, very well cited, heavily cited on every super tree paper. And if not, it's a problem. Okay, now, life is not so simple or maximum triplet consistency. In many cases, actually always, forget about many cases. What you saw now never works, never. Always triplet. What's now? Life is always more complicated. Okay, so let's see complication in very toy example. Let's look at these triplets. Let's look at that same input. Not exactly the same. Let's construct the connectivity graph. 1, 2, 3, 4. 1 and 2. 2 and 3. 2 and 4. How many connected components? 1. Conflict. Okay? Whenever you end up in this stage with one connected component, conflict in your input. What we do? So I remember when I just did my PhD, I had a very, my advisor was something special, and he said that in computational biology, in real life, problems are always hard, and to come and say, this is NP hard, I just sit and scratch my head. So, no. You need to provide solutions, and the MTC problem is find T star that resolve the maximum number of triplets. So this is our goal now, and this is also in real life software. Okay, find the T that resolves the maximum number of triplets, and there are now so many years and so many works on that problem. Okay, so it was shown quite simple proof that this is NP hard, although it was open for a few years, and the reduction is from feedback arc set. It's a simple reduction. Okay, now let's move a little bit to more complicated stuff. So what guys noted is the following. Based on the observation that every edge in the connectivity graph, every triplet, even if that edge is a multi-edge, so it's a multi-graph where edges have, where vertices can be connected by more than one edge, every such edge represents a triplet. So we run that same algorithm. If we get stuck in one component, we compute a min cut. We want to cut that graph such that we violate the least number of triplets. And then once we cut it, once we partition that connectivity graph, we have two components, and we can proceed, reiterate with that recursion. Okay, so let's see that example. So assume we have that input that gives rise to this connectivity graph. Okay, connected. And actually, if we speak a little bit of so when I student like you, PhD student, I remember I played with this because it was interesting. It's really fun. I mean, for me at least, it was really fun to play with this nice algorithm. And I came with this idea. And you see how And you see the intuition between the min cut and the max cut. Okay, so that gives you this, and we will stick to that example later on. So a conflict, and we need to cut that graph. We need to separate these guys, these taxa sets. So we run the min cut. So let's run min cut on here. Nice, no? So we have that cut. We put 1 on the one side. We violated this triplet. We violated it because we separated 2 and 6 on one side and 1 on the other side. So it is violated. And now we ran min cut. Now we violated another one, and we still remain with a connected graph. Connected graph. Another one we violated. And now these two guys agree, so we end up. Let's see the tree that is resulted from this min cut series, a series of min cut. This is the tree. This is the tree. No actual triplet is actually, yeah, these two guys are satisfied. These 3 are violated. Min cut. Now let's see that max cut. So then let's have a look on something, on some intuition that gives an entirely different approach. At every step, when the algorithm is stuck, one connected component, a conflict, some triplets must be violated. However, some are satisfied. Some can be satisfied. Let's not ignore them. There is more signal in the input that is ignored by the min cut that we want to take into consideration. For a triplet ijk, denote the original ij edge. That original edge that we spoke until now as a bad edge. We don't want to violate it. We don't want to cut that edge. So this is bad. However, let's introduce, and these are the bad edges, the original. It is connected. Let's introduce now. Wait a second. Okay. However, let's introduce 2 new good edges, ik and jk. So these are the bad edges that I said, and these are the same, twice the number of good edges. And the key observation here, every triplet, ijk, such that this edge, the bad edge, is not cut, but one of these 2 is cut, that triplet is satisfied. We must violate at least one triplet, but we can satisfy many others. Let's take that into consideration. Again, it's a heuristic. Find the cut that maximizes the ratio between these 2 guys, and then so we violate the least number, or we maximize that ratio, and we can continue. We can continue in the recursion. Okay, so this is the cut here. Very intuitive, no? I mean, one red edge, one bad edge, but see how many good edges we cut here. How many? Okay? And this is why I like this example. The dates, I think, 25 years, 20 years when I was at my PhD. Now let's see. So one must be violated. This one. All these guys satisfies at once, satisfied immediately. So we don't have all these rounds anymore. So in one, like in a sword, we finish the we finish the run, the algorithm. Okay? So one thing to say here, min cut. So again, I was a PhD student. And you play with your time is valuable. And you say, we have the min cut that is polynomial. And it's quite, it was very intuitive. Why to come with this idea? Max cut is NP hard. So we come with some idea that we have no intuition except that observation that we showed, but it's also NP hard. What can be done? And why to pursue that? And as you saw again at the tree of Siavash, this is the root, because it was quite pioneering idea at that time to come with something that is more complicated with no guarantee, and still it turned out to be something very fundamental nowadays, 20 years later. Okay, so this is how we formulate it algorithmically. We look for a cut C maximizing alpha while satisfying this function. So we want to maximize this alpha, which is a ratio between the good and the bad edges. These are the good edges that we want to cut. These are the guys that we don't want to cut. So we want to maximize exactly this ratio while keeping this non-negative. Okay? So we want to maximize that ratio while keeping this. And this you can give to a computer. Okay? So, however, it is equivalent. It can be shown it is equivalent to solving max cut. Max cut is NP hard. Tough problem. However, there are some exact algorithms. What are exact algorithms for NP hard? Approximation. So we have approximation, however, which is in convex optimization, that these are the approximation are polynomial based on convex optimization, however, very heavy as well. Polynomial, but computationally intensive. So we relaxed that and we came with some heuristic SDP, semi-definite programming heuristic. So we base it on the three-dimensional sphere. We relax that. Again, it relates to, who spoke on this, about relaxation, integer programming versus linear programming. So we relax the integrality here, and we solve that. D is the Euclidean distance, so we put it on the Euclidean distance, and we solve that very fast with some heuristics here, fiducia mates. There are heuristics that are destined to work on the continuous sphere, and vertices are partitioned by random hyperplane. Let's see some intuitive example here. So this is the example. Again, that represents our triplet set. This is the discrete, it is the discrete or combinatorial representation of a problem. This is the continuous geometric representation of the same input. This is the sphere. Distances here are Euclidean. We move the points, okay, in order to optimize that function. And now, just imagine you draw a random hyperplane in this sphere, three-dimensional sphere. With high probability, it will separate these guys from these guys because you optimize that function. And this is exactly what we did, what we wanted, correct? So we have some translation from the discrete combinatorial problem here to the geometrical continuous regime here. And this is how we solve. So that is maintained. Now it can be maintained in software, very fast software. And so this is the max cut idea versus the min cut. However, inferring rooted trees is problematic. We don't have that signal of time in the data. So, like I said, the most common, and also you could have seen that either in Siava's talk or in Tandy's talk, ordinary reconstruction infers unrooted trees. So now we are back into unrooted trees, and I remind you, quartets. So triplets are useless in the unrooted setting, and we are with quartets, okay? And the quartet say there is an edge or a path in the tree that splits or separates 1 and 2 from 3 and 4. Nothing more than that. You cannot say anything about distance. These guys can be so far apart and yet separated from these guys. These guys can be very nearby and yet separated from each other. Okay? Just some combinatorial fact. Quartet amalgamation stands at the heart of almost any phylogenetic task. And this is to remember. If you run into phylogenetics, eventually if you dig deep enough, you will get into quartet amalgamation. So from triplets to quartets, no available divide and conquer algorithm, and no wonder, because now it is NP hard. Everything here is NP hard, even if the quartets agree with one another. So if they agree, as opposed to triplets that we have, and this is very classical result by Mike Steele from 92, that actually, if I said that everything boils down eventually to quartets, you get into this. Hard task in general, quartets introduce non-trivial obstacles for working even with cuts. Okay? So what are the results that we came here in 2009? Satish Rao and myself. We extended the connectivity graph to deal with quartets. So first we extended. Again, it will always be NP hard, but we moved it into the graph area. A new independent divide and conquer. Again, NP hard. We will never solve an NP hard problem, but we can represent it as a divide and conquer heuristic. So what is the extension? We have the same bad edges of these guys that we don't want to cut, these guys that we do want to separate from each other. So just have a look. Let's see it here. Just have a look. So assign unitary weights to good edges and minus alpha to bad edges. So we don't want to cut the bad edges. We do want to cut the blue edges. In the ideal case, we will just have these, the cut will be here, vertical, no bad edge is cut, and all good edges are cut. But this is the ideal. We cannot guarantee that to all the quartets. And the idea is, the motivation is like I told you, we will strive to put cherries together and separate between non-sister taxa. Okay, now this is the quartet graph, that multi-graph here. Again, multi-graph, you see more than one edge connecting two vertices. This is bad and good, but the sum of them is the weight of that edge. And now see the problem we have in a triplet is either violated, that triplet, or satisfied, that we separated this guy 1 and 2 from 3, or simply unaffected, goes down to the next recursion. Here, however, we have that. A quartet is either violated, like the two bad edges are cut, okay, violated, satisfied. No bad edge is cut, so it's satisfied, or deferred. This is deferred. We separate one guy, one taxon from the 3 others, and this is the problem. The challenge is how to cope with these deferred edges, deferred quartets. Why? Because now we forgot about the quartet. This guy, 1, went to one side and all the 3 to the other side. How can we take care that down farther below in the tree, we will still separate between 2 and 4 and 3? This is the challenge. And this is the challenge we had to cope with. Okay, using some algorithmic techniques, we could show that if all cuts are found correctly, the correct tree is returned. So if all cuts, which are the cuts, the split in the tree, so the correct tree is returned. Okay. Now I want to, so this is about the theory and the intuition between max cut and quartet and everything. Now, a challenge is to translate all this theory, which is not very trivial, into practice. Again, I remind you, we have here, it started with toy examples, max cut is NP hard, how you really translate that to some software and show that something works here. So quartets arise whenever signals conflict. Can we translate our theory to useful algorithms? How scalable will it be with all these NP hard problems? So I show now some results yet unpublished because so my student Shai was here 2 months before he went to reserve for almost 2 years. So Shai was here and people still remember him and miss him. So he's in charge of that, and since October 7 he's in the reserve, in the army. So this is, and also I told you I'm busy on politics, so this is the politics of the time. In Israel everything is combined. So these are the results that he showed. So these are the first we see that the numbers here, the instances that he deals are significant. It's not toy example. I showed you 6 taxa and the 5 triplets. Shai plays with thousands of species, 5,000 of species, many quartets. He introduced a lot of improvements that he can reduce the command on 5,000 guys, taxa, you have 5,000 to the 4 order, 5,000 to the 4 quartets. That's crazy. That's not in any computer capability. So he was able, you see, he works in the space of log of the quartets, okay, log of the quartets. So this is the space he works in, and he could show very accurate results, okay, very accurate results in very fast running time, okay. This is also here in here the algorithm is the weighted, so he introduced weights to the quartets. Okay, so this is, if you remember, Erin had the W3QMC, so she develops, Erin develops the new generation of quartet mascot. She found it very useful. So this is weighted QMC that we have for 10 years already. So also here the performance is even better, and the weights can represent confidence in signal. Now let's review a little bit of real theory, not these two examples, like asymptotic results. So like I said, MQC is NP hard even when all the quartets agree. So we don't have that algorithm of the AHO, okay, for the triplets. We don't have ideas in general. We don't have ideas. And this is the classical seminal result of Mike Steele that was here in IPAM in 2011. Exact polynomial algorithm exists for special cases only, and the best approximation, if we don't have an idea, we just draw a random tree and we are guaranteed to get expected approximation of a third. Okay, so every triplet or every quartet is by chance satisfied, and that ratio is third. Now, there was some algorithm, a very precise algorithm for the very simple case when all quartets exist in the input, and these quartets do not agree. If we have all the quartets, we know to check that they agree. In that special case, we know to check. So they don't agree, and there is some very exact, so this is very exact approximation that we wish to have always. We at 2010, we improved that not to all the quartets, but if we have all the quartets, divide by 200. So we still produce a PITAS, exact approximation, but we came with this idea that is now again acquiring or gripping acceptance for large, and we now deal with large inputs. For large inputs, we use sampling. We assume some distribution, any distribution on the input. Based on that distribution, we can use the power of randomness. Here we assume all the quartets are sampled uniformly. That uniformity and the number of quartets that gives us a lot of power, the power of randomness, and we could break that third. So we did not solve an NP-hard problem. Okay, we did not crack the question whether there is a better than a third approximation because it is sampled input, but we gave some interesting, and this is based on the max cut. we later on, a few years later, we gave we improved over this for relatively sparse input, although it is dense, it is dense versus very sparse, but it is much sparser than here, okay, so much sparser than here. We sampled MQC, and we could show some very precise approximation. I will skip that. This is our approximation algorithm. I will skip that. This is quite technical. I don't want to delay on this. But like I said, it's the first time to break the bound of a third. And I want now to say some, and here finish there with the theoretical. Let's see how with respect of time. I'll be very fast. Actually, let me skip this. Let me move here. So, like I said, back to biology, horizontal gene transfer, just everywhere, everything, everywhere. CRISPR, gene transfer. If you heard about CRISPR, everything now in microbial evolution that is so much our evolution. Deals with gene transfer, which is the transfer of genetic material, horizontal gene transfer of genetic material, not through linear descent. So bacteria or microbes share DNA through viruses, plasmid, whatever you want, gene transfer, okay? Now, mathematics of gene transfer, very important, very pervasive nowadays. Okay, so these are the significant mechanisms by which bacteria acquire antibiotic resistance, by which they acquire new niches, become toxic. Gene transfer is like almost in bacterial evolution, microbiome. So it's not only bacterial evolution, it's our health, okay? Gene transfer. Now, what are the mathematical representation of gene transfer? So this is how the bacteria evolve. They evolve from one another, so this is vertical descent. However, when a gene is transferred from Klebsiella to Shigella, that gene tree now becomes this way. Okay? So, Klebsiella moved that gene to Shigella, and now Shigella is a descendant of Klebsiella. I hope I pronounced the name correctly. The tree of life now, but this is for that specific gene. So the tree of life is now a network of life. Some gene follow vertically, some gene follow horizontally, vertically here, horizontally here. Entire spaghetti, like they said. So it's spaghetti of life. There is also this term. And now, what can we do? We want to reconstruct the microbial phylogeny. We have a gene tree for every gene. And let's have a look what's going on here. So we have these main routes, and between these main routes that are vertical, we have these thin routes, strings that represent minority of genes that travel between species, okay? And we want actually to capture and return the main trend of evolution, the main vertical trend of evolution that is now in agreement between microbial evolutionists, okay, that we work with quite heavily, that the main signal, the main trend of evolution is vertical. Most of the genes transfer between ancestor and descendant vertically. Okay, wait a second. So we cannot just join all gene trees. It's a hard problem. Again, quartets disagree. A hard problem. Trees disagree. We can decompose each gene into its constituent quartets and construct the super tree of life. And this is some results. But this is one of the papers that we published. This is the weighted QMC. But again, Siavash discussed that approach, and he didn't use that word majority, but majority is something that it can be shown that we can tolerate. So this is a result with Sebastian Roch. Again, this is some, it's not CGSI, but it is IPAM, that was the father of CGSI. So we can tolerate surprisingly large amount of AGT at every gene and still obtain every quartet correctly. And this is, let's see what is how can we do that? So we have, for every quartet, find the topology that is in majority. We call it the majority quartet. So let's have a look at 1, 2, 3, and 4. So 1, 2, 3, and 4. So we see that this violet edge separate 2 and 3 from 1 and 4. So we have for that gene A, we have the induced quartets 1, 4, 2, 3. Now let's look at gene B. We have this quartet. So now let's see 1 and 4. Again, 1 and 4 are separated from 2 and 3. And the last gene, gene C, we have again this separation, 1 and 2 versus 3 and 4. So the quartet that is in majority, or the topology that is in majority among 1, 2, 3, and 4 is this one, 1, 4 versus 2 and 3. So we take that quartet, 1, 4 versus 2 and 3. We take that. Okay? Actually, in a secret, I can tell you, we also take that. They conflict, but we know to deal with conflict. But anyway, this is the majority quartet. The proof, the theoretical proof is over this, over the majority quartet. And the theorem says that if this is the intensity of HGT with some more assumption of uniformity, so the entire species tree is bombarded with HGTs uniformly. Okay? Then the topology, the majority that is in majority, is the correct one. So we take the correct quartet. Now we have all the quartets. If they are correct, they agree with the big tree, and we know how to join them. They agree, but if you have all the quartets, as I said, we know how to join them. The correct tree can be reconstructed efficiently. Let's just keep that. This is another issue that was discussed in the retreat by Leila about tree distances. Let's not exactly. Yeah. Let me conclude. Max cut is superior over min cut. Nowadays, I should change that slide. Min cut is just for illustration, for more teaching, but not no one really. Now it's max cut, or just the only criterion that is in consideration. significant advances in analytic results. So there is even newer results that now not by us, which is surprising, and crucial component in gene phylogeny, ongoing project, 3 distances under partial information, quartet plurality, like I said, open problems. Here there was a recent very significant progress. And let me acknowledge, so the quartet was, I started the quartet with Satish Rao from UC Berkeley, Rafi Yuster from U Haifa with myself, Sebastian in Wisconsin, Chris should know him, Tandy Warner that was here, my student Eliran Avni, Shai, Reuven Cohen. This is the funding. Eliezer, where is Eliezer? Eliezer always, I mean, by default, Eliezer is always on any acknowledgement. That's a problem here. I mean, I apologize, not for Eliezer, for you, because he had supported everything in my life here. And that's it. Thank you.